Okay, so I'm sure you've all seen this one a squillion times now. So this is the facility, and then I'm just going to zoom in on. I'm going to zoom in on the on this bit, which is the bit we're talking about. So this is the target. So we start off with protons. We put protons onto the target. We make pions. The pions go through a chicane. We select out the mesons and chuck away the protons. Then we go through a longitudinal capture system, charge separation. So somehow coming out of this longitudinal capture, we have a whole load of bunches. So we merge those bunches into one mega bunch, and as we had discussed on some of the other days, a mega bunch has more luminosity than lots of little bunches. Then we cool that mega bunch down even more. We go into even more cooling, the final cooling, the buncher, and then we go into a sort of acceleration system, and then we go on to the main acceleration. So okay, so this is the target system. So we take protons, the protons hit the target, we make pions, pions decay to muons. So in here we have a block of graphite, and that graphite target takes the proton beam. So the graphite target, there are a few problems with doing it this way. It's how the neutrino people do it, but you have a huge power going onto the graphite, which needs to be cooled. And then it also causes lots of stress in the target, and it also makes a big dose of radiation, which goes onto the surrounding equipment. And so out here you have a superconducting magnet. The superconducting magnet does not like radiation, and so we cook the magnet, which can cause a problem. So this is an example of the radiation dose which we get on the magnet. This is actually a slightly older design. So in this one, actually the target was at an angle. You have the protons coming in at a slight angle. You have the beam coming down here. This region is at room temperature. This region is cryogenic. So you have loads of shielding, which sort of protects your cryogenic equipment. Nonetheless, you're dumping power onto the cryogenics. The magnet doesn't like it. It can damage the magnet, which we're scared of. So there's insulation in the magnet which gets degraded, but also we need lots more cooling. And then depending on your cooling power, depending on your cryogenic equipment, you end up using a lot of electricity to cool this cryogenic equipment. And sort of typically people talk about 10 to the 3 or 10 to the 2 inefficiency in terms of cooling at cryogenic temperatures. So 1 kilowatt of heat makes 200 kilowatts of electricity. And so the way we're addressing that is we have high temperature superconductors in the solenoid. We hope to be designed or being designed, and we think it works. And it looks rather like a fusion magnet. And we have fusion magnet companies, as Luca said, who are quite interested in that technology. Okay, so then after we come off the target, we go through a chicane. And so the chicane is used to get rid of all the junk. So it removes high momentum particles. Then we have a beryllium plug down here, which ranges out the low momentum impurities. And then we go into this longitudinal capture system. Okay, so our chicane has no dipoles. It only has solenoids. The solenoids go around this sort of nice bend. And what happens is, if you imagine you have your, I can draw it on the board even. So you have your solenoid field lines. This is sort of what the chicane looks like. So these are field lines, okay? Solenoid field lines. So your particles are going round. Maybe I should do the particles in a different color. Particles are coming round. Now, as the particle sees a radial field, so there's a radial field component and a longitudinal momentum, the particle gets a kick in the vertical direction. So what happens is, if I now look sideways on, our beam is going to walk along. It hits that radial field component and it gets kicked up, okay? The negatives are going to come along. They again hit the radial field component, but they have the opposite sign, so they get kicked down. And then we get to this point, the radius of curvature changes. So actually the radius goes in the opposite direction, and they get kicked back down again, and they end up going back in a straight line, which is good. And then the high momentum particles, which we don't want getting into the rest of the system, the off momentum particles, which we can't use anyway, so we just want to get rid of them, they actually go up and they hit the walls. They're not captured. Now, the really high momentum stuff is so rigid that it doesn't see these fields at all, and it just comes straight through. And so so then we have the really high momentum primary protons, and they just come straight through and come out the system. And so what we're trying to design at the moment, and we're still working on the design, is somehow some sort of system like this, where we really have the good particles coming around the corner, the low momentum cruft hits collimators and we get rid of it. The high momentum stuff, which we can't collimate because it's so energetic and so powerful, we take down a secondary beam pipe. So that's the sort of design we're working on. It's still a work in progress, but that's the concept. Right. So and then just for the pictures. So what I've got here now, this is in the middle of the chicane. This is the position, horizontal and vertical, for some particles, mu plus, I think, but one side of particles. There's some particles in the middle which are reasonably well behaved, and then you get this stuff which is off momentum, where we've designed the system to have a momentum cut of about 500 MeV over C. So these ones get lost; they hit the roof, and that's by design. We've designed it to have a 500 MeV over C cutoff. And then the beryllium plug. So the reason the beryllium plug works is it actually comes down to the DDX curve. So you recall the DDX curve goes with momentum. So that means that anything that goes with beta gamma rather. So beta gamma for protons of a given moment for protons will be much lower than beta gamma for muons, given which make it round this corner. So that means protons will get stopped in a much shorter distance. They're right on that horrible rising part of the DDX curve, which I showed this morning, whereas the muons and pions are on the sort of minimum ionizing part of the DDX curve. So the protons get stopped in the plug. So what you can see here is this is a residual beam power which makes it round the corner. And if you choose your parameters right, you can suppress the junk protons by like 10 to the minus factor of 10 to the minus 2. So protons cause radiation. They don't give us any good particle yield. We just need to get rid of them, otherwise we can't run the facility. It's too much radiation. Okay, so this is the Neuffer bunch phase rotator concept. So we have so we've gone through the chicane, we've gone through the beryllium plug, and now what we do is we let the particles drift out, and then we slowly bring on RF. And we have to carefully, we actually have to change the frequency of the RF to make these little micro bunches, and then dephase the RF to somehow bunch the beam. So this is where I'm going to do my first animation, and we'll see. I'm going to use the back button. I should. Do that. Right. Let's go for this one. I don't know. It may not share, but anyway, it's okay. So this is now. I start off with the bunch coming off a target. So when I started, the bunch was vertical in energy time. So you get this big energy spread, all of the stuff coming off the target. You know, all of these hadronic interactions just make this big energy spread. We have a very short proton bunch, a few nanoseconds long. So the proton bunch is basically zero length in time, like say a few nanoseconds. And what I have, so I have two particles. There's one up here, you can see in dark blue. There's another one down here, also in dark blue. And so those particles are going to be my reference particles. And what I'm doing is I'm choosing my RF frequencies to make sure that even as those particles drift out, they always sit so that they're in a bunching mode of the RF cavities initially. And so what that means is that I'm always changing my RF frequency, and I get these little micro bunches building up between them. So between these two cavities have 1, 2, 3. These two reference particles have 1, 2, 3, 5, 6, about 8 RF periods. That's an input parameter, and And so by choosing 8 RF periods between, that means that I get 8 of these little micro bunches between. It's going to come around again. Right. So let's watch it. You've got the 2 reference particles. I have a frequency up here. At the moment, I have no voltage. So the frequency just tells you that that if I have this frequency, there are 8, I think it's about 8 micro bunches between each of these 2 reference particles. And when it gets to about 325, I think, I gradually start bringing up the voltage, or 400, there you go for this one. So I'm bringing up the voltage, and what happens is you start getting these RF buckets forming. I think I showed a picture like that on the first day, where the particles somehow get swallowed into the RF buckets. And then when it gets to about 10 or 12 megavolts per meter on the voltage, I'm going to dephase the RF cap, the frequency. So just choose it slightly dephased. So this reference particle is at a slightly accelerating voltage, and this one is at a slightly decelerating voltage, which means this one gets moved down and this one gets moved up. And so we end up getting these sort of relatively nice bunches, which we can then push into the cooling system. Yeah. Okay, I'm going to go back to the slides. Okay. Right. Oh, boom, boom. Okay. Animation, good. Right, so the muon cooling I covered this morning, but just to remind you, so we start off with the rectilinear cooling system. So that was this one with the A region and the B region. So the emittance, transverse emittance on the horizontal axis, longitudinal emittance on the vertical axis. So this is the one which has the longitudinal cooling. So it has the transverse longitudinal emittance exchange and the transverse cooling. So the emittance goes down to here. Then we go through a merge. So we have 20 or 20-ish bunches coming down through this system. You remember we've got all those micro bunches coming from the front end you just saw. Then we're going to merge all those micro bunches into one mega bunch. And then we're going to cool that. That means the emittance increases. Remember, we can't compress emittance. So emittance has to, if we put all these bunches on top of each other, the only way we can do that is by spreading the emittance out so that they're not on top of each other, because emittance is incompressible. So we get an emittance increase, and then we go through more cooling, we get an emittance decrease. And then we go into the final cooling system, and as I said this morning, final cooling is just transverse, so we get a transverse emittance reduction, but actually we get this longitudinal heating from the Bethe block curvature and so on, which causes the longitudinal emittance growth. Right, so the bunch merge. I want to go into a little bit more detail about the bunch merge. So we actually have 2 different blobs. So I'm going to start off with the longitudinal bit. So what happens is we have these, we have 20 bunches. I'm just showing one section of 6 bunches of this RF system. And so by choosing RF frequencies carefully, we have the bunching frequency, but we also have a third harmonic, which means that this bunch gets accelerated and this bunch gets decelerated. So we actually have a big RF bucket as well as the little RF buckets. And so we're going to move this bunch round, they gradually move round, and then eventually they actually rotate all the way around and they merge together into one big bunch. So we've now gone from our 21 initial bunches down to these sort of triplets, which means we've got 7 bunches now. Okay. So then what we do in the next section, we have a transverse kicker. So that's this system here. So what it's actually a dipole field which is rotating in time. It rotates magnetically, not physically. So you kick different coils to get it to rotate in time with a frequency so that the first bunch is kicked, let's say, upwards, the next bunch is kicked sideways, the next one kicks sideways, and so on. And you kick them into 7 different transmission lines. If you look here, this one's quite short. This one's actually longer, goes around a bend. This one's longer still. So by choosing the length of these transmission lines, you actually end up delaying the first bunch and compared to the 7th bunch, let's say. And then you bring them all back down together into one, what's called a trombone, and you paint them onto each other in this way. So you got 1, 2, 3, 4, 5, 6, 7 bunches. And like I say, emittance, you can't superimpose the bunches. You have to sort of stick them together and paint them into a picture like this. So that's why we end up with these 7 bunches. Okay, and that means you have emittance growth, you have emittance increase, but by design, deliberately. And then we go into the next rectilinear cooling system, which I already talked about. So finally, we have to go into a reacceleration section. So the deal we did with the acceleration people is we said, or I was told by Daniel, we will give them a 250 MeV beam. So we own the first little bit of reacceleration in the front end. So now there's various different ways to do acceleration at low energy. So this is an example of a low energy electron linac, very high current electron linac. What you have here are these are essentially very low frequency pulsed RF devices. So they're sort of like RF cavities, but they're not resonant. So it's something called an induction linac, or they're not very resonant. And with an induction linac, you can typically get about 3 MeV per meter accelerating voltage. So we can bring the beam up in energy with about 3 megavolts per meter. This is one called Radlac, which was built in the 70s or 80s, and they got 3 megavolts per meter for a 50 nanosecond pulse. If you want higher gradients, you can do it, but you have to make the pulse length shorter. So this 3 megavolt per meter sounds reasonable. This is the H- ion source and linac for linac 4, which they which they built at CERN a few years ago. So they can get, again, in 19 meters, they can get 50 MeV of acceleration, but they weren't running at very high frequency. So we need to chop up a bunch coming out of the final cooling is very long. So we'd somehow need to put the bunch into a low frequency structure, either chop it into little sub bunches again, which is a pain, or something else. That should be a beat. So the challenge of doing proton acceleration is that your beta relativistic is changing as you go down the linac compared to electrons. One of the advantages we have with muons is they're 10 times lighter, which means that you can get up to relativistic energies much more easily. So somehow what I've assumed for the parameters document is that, well, maybe we can't quite do this, but probably we can do a little bit better than this, even allowing for the RF frequency. So I sort of assumed 1 megavolt per meter gradient is about right, to be confirmed or to be seen. Okay, so that's the muon production, rattling through it. I want to talk about some of the experimental validations we've done, and maybe in the context of the discussion this morning, it may be useful to see. So this was mice. This was the muonization cooling experiment. We finished taking data in 2017. We published in 2020, and again in 2023 or 24. I forget quite which. And so we took single muons, because we didn't have high intensity, through the equipment. We measured the muon position and momentum upstream. We measured the muon position and momentum downstream, and then we had an absorber and some reasonably strong focusing in here to bring the beam down to a focus so that we could get ionization cooling. And as you remember this morning, emittance is just some of an ensemble of position and momenta. So actually we measured individual particles. We added up the position and momentum of individual particles, and we used that to really build up an ensemble of particles and calculate an emittance for that ensemble of particles from the system. We had no RF in there, which is important to note. So we had some instrumentation upstream. We took the beam down, we put it through the spectrometer, went onto a tight focus. This is an absorber. So we had 2 absorbers. We had a liquid hydrogen absorber, which is shown here. We also had a lithium hydride absorber. Went down through another solenoid and then down through the downstream instrumentation down here. So one of the features which we had was that this coil was damaged during operation, which meant that we had, so this is the magnetic field BZ as a function of Z. And you can see that you have this uniform field region, or reasonably uniform field region, where the upstream tracker was, but actually down here, we had a missing coil, and that meant it was supposed to be have odd symmetry about the focus point. We lost the odd symmetry because this coil broke, and so that means when you look at how the beam evolves, it doesn't have a nice focus on the absorber like we wanted. In fact, to make the thing work with a broken coil, we actually had to focus just upstream of the absorber over here, and we wanted to have just here we got a nice flat sigma x, nice flat beta function, transverse beta function going through the upstream instrumentation. We want to have the same thing down here for the downstream instrumentation. Again, because we lost the spectrometer, the coil, we weren't able to do that. So we actually had beta. We had the beam oscillating as it went down through the downstream instrumentation. So it is what it is. That's what happened. As Elias mentioned, even the LHC with all of their amazing magnet people has some problems with their magnets, and of course, we also had some problems with our magnets. So these things happen. So okay, so here's a picture of the magnets. So we had two different magnet assemblies. We had the focus coil assembly, which is shown here. So in this box there was an absorber. You have a coil here and a coil here that provides the focus down onto the absorber. We have the spectrometer solenoid. The spectrometer solenoid gave us the uniform field for the instrumentation, and also gave us the match coils, which we wanted to match our beam onto the focus, into the focus. So the way we're doing it is, if you remember this beta function, the second order differential equation, the beta function we talked about, we actually have, if I just go back, so let's say we have a uniform field here. So, and as I said this morning, that means that we set beta double prime and beta prime 0. And so we can calculate what the beta function is here. We have a focus here, and this focus coil we use for choosing the focus. And then we need to choose beta and beta prime. We have these two match coils, which let us actually choose the optics going to here. So we change the currents in these two coils. We change BZ in order to choose how that double second order differential equation evolves in order to bring our beam down to the absorber. And so that's what the spectrometer solenoid had inside it. Sorry, this is the spectrometer solenoid module, and this is the focus coil module. Here's a picture of the absorber. So as I say, we actually had 3 absorbers. We used a liquid hydrogen absorber. We used lithium hydride absorber. We tried doing 6D cooling. In the end, our instrumentation was not up to the job of measuring the momentum, so we weren't able to show 6D cooling. But nonetheless, we showed 4D cooling, which was good. To be honest, the 6D cooling concept was a bit of a bolt-on at the end, and the instrumentation, because of the problems with the magnet, was not running at the level which we wanted, which is why we were not able to complete that task. So in terms of amplitude, so I talked about, again, amplitude this morning. So what this is, I'm looking at these ellipses, I'm counting the number of particles on a particular ellipse to make an amplitude, and then I'm going to histogram it. So this histogram is the histogram of distance from the center of the beam out to the edge in this normalized coordinate system, which is like the single particle emittance or the amplitude of the beam. Okay, so the idea is then that the ionization cooling reduced the transverse momentum spread, as we know, and so what we want to see this amplitude distribution shrink. So we want to see the amplitudes go towards the middle. That's the signal which we're looking for cooling. The mean of this distribution, I didn't do it in the maths, but the mean of this distribution, incidentally, is the RMS emittance. So what's in this plot? So I'm showing down here, this is the transverse amplitude. And what I'm showing is the ratio of the number of events downstream to the number of events upstream. So the signal which I'm looking for is there are more events downstream in the core of the beam than there were upstream. So that means that I move beam from the outside to the inside. So now there's 4 different rows. So this row here corresponds to no absorber. We just had the windows for the liquid hydrogen vessel with no hydrogen in. In this row, we injected hydrogen. And then in this row, we have nothing at all. We don't even have the windows. And in this row, we have the lithium hydride absorber. Okay. And then we have 3 different emittances, nominal emittances. We have a 4 millimeter emittance, a 6 millimeter emittance, and a 10 millimeter emittance. So then what's going on out here? So out here, we actually have a decrease in the number of particles in the tail. Now, mostly that's because we're scraping. So those particles are the particles which hit the wall. There's not actually many particles there, but this is the ratio. But it means that we see a decrease in the number of particles out here. And you can see the decrease is stronger for the high emittance beam because there are more particles hitting the wall in a high emittance beam. It's a beam which has more particles out near the wall, near the beam pipe. And then in here, when we have no absorber, or even just some aluminium windows, you see a little bit of heating. So this is actually showing that some of the particles are actually, there's actually there's not really any effect at all. So basically this is consistent with a ratio of 1. Here you see maybe there's a little bit of heating, so the ratio is below 1. That means they're actually getting particles moving out over here. Here the ratio is 1, here the ratio is probably about 1 as well. So that means that you're not really seeing any effect at all when you have no hydrogen in. When you put hydrogen in, you actually see an increase in the number of particles in the center of the beam. Most pronounced at high emittance, because that's where we're way above this equilibrium emittance, but you do even potentially see some effect at low emittance. Same goes for no absorber and lithium hydride. Again, we see an increase in the number of particles in the core of the beam for lithium hydride. And just so you know, the blue curve is data, the red curve is Monte Carlo. So the data in the Monte Carlo are consistent, so we believe our models. So we saw cooling, so that's good. Later on, we also made this publication. So this is actually showing emittance at the upstream, and then this shows the change in emittance. So what you can see is if there's 0 change in emittance, that means that we have no cooling. If there's an increase in emittance, as we see for the low emittance beams, that means we're below the equilibrium, so we're actually seeing heating. And if you see a decrease in the emittance, as you see for the larger emittance beams, that means we're seeing cooling. The straight lines are theory lines. The blue is data, the red is Monte Carlo again. So the data in the Monte Carlo are consistent with the theory, within errors, of course. And then this one's the one with the absorber in. This one's the one with no absorber for liquid hydrogen. Same for lithium hydride. This one's absorber in. This one's no absorber for lithium hydride. So things are behaving as we expect, and we think we see transverse emittance reduction. So this is good. Life is good. So where do we go next? Well, we'd like to do next the cooling demonstrator. For the muon cooling demonstrator, the aim is to build on mice. We'd like to do both longitudinal and transverse cooling. Remember, we only saw the transverse emittance effect in mice. We'd like to include these RF cavities to reaccelerate the beam. We'd like to chain together multiple cells, and I think we want to demonstrate routine operation in an accelerator style operation mode. So mice was more like a particle physics experiment, which is fine. You know, it's good for a proof of principle, but you'd never run an accelerator like that. And just the conceptual design, or pre-conceptual, very conceptual design. We take beam off a target, we take it through some sort of preparation system. Then we go through an upstream instrumentation system to characterize the beam. Then we go down through this sort of rectilinear cooling system and then into a downstream instrumentation system. And we compare, in principle, the emittance in versus the emittance out and check that the system works. And just to compare it with mice, so in mice, we cooled in 4D. In the demonstrator, we'd really like to do 6D cooling, so we'd like to demonstrate this emittance exchange process. In mice, we had 1 absorber, whereas in the cooling demonstrator, we'd like to use many absorbers. In mice, we didn't even really have a single cooling cell, whereas here we'd like to see many cooling cells. In mice, we didn't reaccelerate. Here we'd like to reaccelerate, and we'd like to use a bunched beam more like an accelerator beam, and instrumentation more like accelerator instrumentation, where we use electromagnetic interference, or we really look at the multi-particle bunch properties rather than single particle bunch properties. Okay, I've shown some of these pictures before when I was talking about the rectilinear cooling system, but this is the sort of parameter space we're in. So this is the optical beta function. This is the solenoid field strength, dispersion. This sort of schematic of how the cooling cell looks. Actually, I think in the end we've got 3 RF cavities rather than 4, but otherwise This one's a couple of years old now, but we're pretty much in the same place. So it's sort of so that's good, and we're going through the engineering now for actually how we build this. This is the performance over a sort of few tens of meters stretch. See, we get a decent 60 emittance reduction. We get a longitudinal emittance and a transverse emittance reduction. This system's optimized for a relatively high transmission. If we went for a lower transmission system, then we might be able to get more cooling at the cost of some transmission. And one of the things we want to do is we actually want to measure a low transmission but big cooling section and compare that with a high transmission but less cooling section. And these sorts of parameter scans are important to do. Okay, so then wrapping that into a program. So we'd like to start with some RF tests because one of our main concerns is really about how the high gradients which we would like for the ionization cooling. The higher the gradient, the quicker the cooling is. So there's some advantages to doing high gradients. As we start developing the RF technology, we'd also like to look at the integration of an RF of a cooling cryostat. So, for example, can we really put these solenoids, cold solenoids, next to the warm RF? Can we handle the forces between these systems and so on? Install a absorber there as well. Then take something like this, put beam through it, and then set several of these cooling modules in a row and put the whole system through with beam. And then, so that's obviously quite conceptual. We've started doing the optics design, this one which Paul's working on. This is actually the TT7 design. We're looking at another one in CTF3 as well. So we have a target like this. We go through a series of quadrupoles, dipoles. We have a beam dump to take the primary protons and clean them up. And then we go around to a beam preparation system and off into the cooling channel. And as I say, there's another design which is looking at CTF3, which is another area on the CERN campus. We're also looking at potential hosting options on the Fermilab campus, where there are various different sites which are under discussion. So you can see these purple numbers. These are all different candidate sites with various different advantages and disadvantages. And we're still at the sort of optioneering stage, I think, on the Fermilab campus. But nonetheless, there's a lot of interest there. One of the things people talk about, it was asked in the questions maybe on, I can't remember which day, maybe Monday, is the idea of going in with a neutrino facility. So people occasionally talk about whether or not we can do something with NuStorm. So I thought I'd put the slide in. The concept would be that we share the target. We take the muons off into the cooling demonstrator, and then we build out this cooling ring. Sorry, not cooling ring. We build out this ring over here. And we let the muons decay to neutrinos. We have a neutrino detector. The idea would be to measure the neutrino scattering cross-section, and that helps the Dune folks and the T2K folks with their analysis, and maybe we can improve their resolutions. There's also options for BSM physics in that as well. One of the motivations for doing NuStorm is somehow if you look at the muon beam power, as a in terms of what's been achieved and what might be achievable in a facility, you've got sort of relatively low muon beam powers have been achieved to date, and you'll sort of want to push in this direction along these diagonal lines to get to higher muon beam powers. So this NuStorm facility would be, I think, the highest beam power muon beam ever produced for a facility. So somehow you want to push in that direction to kind of convince yourself you can do muon beams. Okay. Good. So I wanted to go through some of the alternative technology options to finish up, because somehow, the cooling system I presented has some flaws and it can be further optimized. But I think one of the very important things with the muon collider is the technology is very fresh, and so taking different angles into how we do the muon cooling, I think, can yield some very strong improvements in the performance of the facility. Somehow the proton and electron world, they've been developing proton and electron machines for the last 100 years, and it's very hard to imagine a new technology coming up now, whereas muon machines, really, we've only been looking at it for 10 years, if that, depending on what you mean, but really there's only been a handful of people looking at it. So it's a much less mature technology. So I want, and so I want to sort of, motivate some of the history and remind people of some of the other technologies which are out there and which may still be very relevant. So one of the first concepts which was developed was this idea of doing a cooling ring. So the concept is that you have a ring, obviously, and you recirculate the beam through the same absorber. The reason that's good is because the cooling system in the collider as proposed is a significant fraction of the cost. It's not half, but it's significant. And so somehow reusing the absorber, reusing the RF can have significant cost savings. The problem with the cooling ring, the reason why people did look at it before and they kind of got frustrated is because the injection and extraction is very tricky. So a typical rise time on a kicker is 100 nanoseconds, and speed of light is 300 millimeters per nanosecond. So that means you're looking at a sort of 30-meter circumference for a cooling ring for a reasonable injection system, kicker injection system, without doing any clever optimization or anything like that. So then if we just compare this 30-meter, thumb in the air type length, and you compare it with the length of each of the stages in the rectilinear cooling system, you can see each stage, well, they're sort of 100 meters long, 30, 40 meters long. So maybe out here, it may be productive to look for a cooling ring, but sort of somehow when you're getting down into some of this stuff, you think maybe a cooling ring is less useful. So to be studied, of course, and maybe you can do some better job, but that sort of gives you a flavor of the sort of constraints, and why cooling rings have not been aggressively pursued, but maybe they can save a factor 2 in cost, for example, which would be very valuable. So another concept which is under study at the moment is this idea of an HFOFO cooler. So this is the idea is that you have solenoids just like in the rectilinear cooling channel. In this scheme, they use tilted solenoids to make a dipole field, but you can just do dipoles as in the rectilinear cooling channel. But the difference is they set up the dispersion vector, so the dispersion vector advances every 3 cells. And what that by 120 degrees. So the concept is, you imagine your dispersion vector on the first cell is like this. So this is Y, this is X, or D, dispersion in X, dispersion in Y. So this is like the nominal momentum particle is here. A particle with slightly higher momentum is over here. So that's what I mean by the dispersion vector. Dispersion is, I'll get it wrong, it's dx by dp times p. Someone will correct me if I got it the wrong way up. So that's the dispersion vector on the first solenoid cell. Then it advances by 120 degrees, and then it advances again by 120 degrees. So now for the positives, you do that in this direction. For the negatives, you do it in the opposite direction. So the negatives are going around. So the negatives will start here, and then they'll come around in this direction. And so if you put your wedge absorber here like this, on the first cell, you'll get a bit of wedge cooling the negatives and a bit of wedge cooling the positives so then if you choose your advance of the dispersion correctly, you can put a wedge here where it will cool both the positives and the negatives as well, and you can put a wedge here where it'll cool both the negatives and positives as well. And so in this way, you can cool both sign muons in the same system. Again, it's a factor 2 in cost. So it's, factor 2 in cost makes a difference between sort of, makes a big difference in the facility cost, obviously. A concept they looked at, which looked very nice and almost got the same cooling performance as the rectilinear, but not quite, was this idea of the helical cooling system. So the helical cooling system was sort of based on this thing they have at RIC called a Siberian snake. So what you have is this sort of solenoid, continuous solenoid dipole, and the muons travel along the axis of this helix, and inside they're going around in a circle, and you get a very strong dispersion vector. So you get a very nice cooling performance. Now, the RF cavities here would be rather small compared to their natural frequency. So the way they plan to manage that is they actually put dielectric into the RF cavities. So So just to remind you the way RF works, so if you have an RF cavity, oops, there's your beam pipe. It's a resonant box. So typically you use it with, that's your electric field. So somehow this is a resonator, and the speed of light determines the wavelength, which determines the size of the box for a given frequency. If you put some dielectric in here, that has a refractive index, which means that you can actually get something like this. You can make your cavity narrower. You can have a cavity which is narrower. You put lots of dielectric in, then you can get a much narrower RF cavity for the same frequency. So you change the resonant frequency, and that's the concept behind these dielectric loaded cavities. And then to cool the beam, the concept was to put high pressure gas in. The high pressure gas acts as an insulator, so it stops electron production, stops sparking in the cavity, so potentially you can get higher voltages as well. Okay, so this is something they've built and demonstrated at PSI. So this is what they call the high intensity muon beam line. So they're working on improved muon beam transport, but the interesting thing for us is this cooling system. So the way it works is they have a complex system of electric and magnetic fields, which actually gives a compression of the longitudinal beam by what's called frictional cooling. So in frictional cooling, so this is the beta, I'm going to draw the beta block curve. So I showed it this morning. I have a beta block curve which goes like this. So this is beta gamma. This is d E dx. Now the trick is, up here, it turns over. And so what happens is you actually get to a point where the energy loss is well, yeah, the energy loss is actually going in the right direction for longitudinal cooling. Now this beta gamma corresponds to beta equals 0.01, so 1% of the speed of light. So it's quite slow. So you need to get, so you can cool very low energy muon beams. That's interesting for some applications. They want these very low energy muon beams. So this is the low energy muon beam line, which they're developing at PSI. And they've demonstrated this sort of system experimentally. So another system which they're developing at JPark is the laser ionization cooling system. So in the laser ionization cooling system, they take positive muons, they put the positive muons into an aerogel target. Inside the aerogel target, the muons pick up an electron and stop. So you end up with thermal muons, few electron volts of energy. The muons drift through the aerogel, and then they come out and they get hit by a laser. The laser zaps the muons, knocks the electrons off, and you get ultra cold positive muons. So that's what they call laser ionization cooling. Again, they've demonstrated it. They're going to use it for G-2 experiment. What they've done at the moment is they've constructed and operated it at JPark based on whatever stuff, very nice experiment, but they used existing equipment. What they would like to do next is actually upgrade for efficiency. So that means buying new equipment to improve their efficiency. So at the moment their efficiency is quite poor, but they expect to improve it as time goes on. And really it's about this laser, how much laser power they can bring onto the muons to ionize them. Okay, scheme ISIS, which we're working on. The idea is that we take low energy muons again, going through a low density gas. As muons go through the gas, they lose energy and thermalize. We actually additionally put a decelerating RF pulse, quite a short RF pulses to really pulse the muon beam and stop them. And then we have an RF pulse which is lagging the muons to reaccelerate them. Oh, I have another animation. Let's see. this one. Okay. So what I'm doing the usual weird accelerator thing where I take Z as my independent variable and I'm freezing the beam in time, and at each frame I have a picture of the beam in time. So looking at in time, I have this RF pulse out here. That's my initial decelerating RF pulse. And then I have this RF pulse over here, which is the one which picks up the muon beam and moves it along. And so what you get, so the initial muons get slowed right down. It's a 3D distribution, so some of the muons are just spinning in the solenoid field, which solenoid focusing field. So that's why you get these sort of high energy particles which don't appear to be doing anything. They're just lazily spinning around in a circle. They're not making a helix at all. They just have circular motion. And then, but the ones which get decelerated, they stop. And in helium, muons do not pick up an electron because helium preferentially binds to the electrons, and muons don't like picking up electrons at all from helium. So we actually stop the muons, and then this RF pulse comes through later and takes the muons. And again, we're keeping the muons down in this part of the DDX curve. So the RF pulse moves along at beta equals 0.01. So the muons could never accelerate faster than that, which means they just get cooled down on this RF pulse. We can bring them along. We can get to a very high intensity. So this is basically a zero energy spread beam, not too bad on the time spread. So we get a very nice narrow beam that way, which is great for the mu-SR people, but also might be useful for a muon collider. In terms of challenges, it's just about at the worst point on the Paschen curve, so we can induce RF breakdown. We actually pull electrons off the helium gas and break it down. And also I'm looking at the energy straggling model in my simulation because GM4 can't do this because it doesn't like stopping particles. So I have my own tracking code which I'm using. So somehow there's still work to be done, but it looks quite interesting. So in terms of the JPark scheme and the ISIS scheme, this is the emittance performance which I showed before for the baseline, and then the scheme this ISIS scheme which we're looking at goes from up here down to over here, and it's got a reasonable transmission, sort of 50% transmission in this acceptance to be seen whether we can sort out energy straggling and so on. And then if you can make the laser ionization cooling scheme work, you're right the way down here in emittance space, which is very interesting. But they're still working on their efficiency for their scheme. To be seen whether they can get the efficiency up high enough. Nonetheless, you know, there's interesting work going on in this very low energy cooling space. Okay, a couple more technologies which people have discussed, which I wanted to bring up. So in terms of cooling, we get more cooling if we get more focusing. There's two focusing technologies I want to raise to finish off. The first is the lithium lens technology. So this was used at Fermilab for the antiproton production. So the concept is that you have a lithium plug. You put a current through the lithium plug in the azimuthal direction, and you make a magnetic field in the you put a current in the longitudinal direction. You get a magnetic field in the azimuthal direction. And that's like a target horn, which you may be familiar with from the neutrino people. And that gives you symmetric focusing both in horizontal and vertical. It's single sign, but nonetheless you can get rather strong focusing. And it's a technology which has been done. So people have built this and used it in anger. So that's quite interesting. The other concept which I wanted to raise is the concept of a Gabor lens. So in a Gabor lens, what you do is you have a solenoid which is wrapped around a voltage trap. So you have electrons sitting inside your voltage trap. You put your ion or muon beam in the side, and you get very strong focusing from an electron cloud. So a Gabor lens may also make an enhanced focusing. You know, people talk about factor 10 or factor more on the electron focusing compared to solenoid focusing. So that's also a very interesting technology which may let us get down to more cooling. Okay. So that's all. So we've looked at the major components of the muon collider production scheme. I looked at alternatives, I looked at some of the experimental stuff. The reason we chose the baseline is not necessarily because it's the best, but it's because it's the best developed. So there may well be better schemes out there. I'm certain there are actually. I don't think we've got the best cooling scheme that's possible, But somehow what we're in the process of at the moment is trying to prove to our colleagues that we can do it. Once they believe we can do it, then maybe we can leverage more investment. And at that point, I think this can take off. So there are lots of interesting options really for developing the technology. It, of course, needs effort. Okay, so, and then to finish, maybe, I don't know if Roberto wants to say something, but it's sort of somehow it's my privilege to give the last lecture at least on this part of the workshop. So I think I want to just say something about the muon collider in general. So the muon collider, I think, has far higher energy than E plus E minus colliders, a far smaller footprint than equivalent proton colliders. So that's very important, and somehow it's really a very interesting technology, I think, to push. There are lots of technical challenges. You've seen a lot of them this week, and it is very challenging, but all of the challenges are manageable with current or near to current technologies. So what we've got to do now is really demonstrate that. We've got to demonstrate we can build it. Somehow, I think the muon collider has the potential to advance particle physics by many decades. If we could do it, it would really be a historical achievement, on the scale of proton acceleration or electron acceleration. So I think we should do it, and I think we must do it. And that's our challenge for the next decades. So thank you.
I will provoke you, maybe with one of the last things. So this story that you have only one bunch, and also you discussed at the beginning that you are basically, merging bunches, etc. Am I completely fool if I think that there is room to make a multi-bunch beam? And don't laugh at me. Think about a high luminosity muon collider at some point.
Yeah.
Maybe along, in 1 century. But
so the JPERC proposal, they have a proposal out there called Tristan. And actually they don't, so where they're using this very low emittance beam, and this beam would get completely destroyed by all of the collective effects which Elias kindly told us about earlier. So their proposal is in fact, again, indeed to make several muon bunches and then collide with electrons. So these low energy cooling schemes only work with positive muons. Negative muons get bound to the nucleus too strongly, so you can't use negative muons. But you can make positive muons in this way, accelerate them to very high energy and collide them with 60 GeV whatever electrons. And so that's the proposal from JPERC. And then, yeah, maybe multi bunches, sort of hundreds of bunches with this tiny thermal emittance traversing around your machine. Yeah, maybe.
Before I ask better my question, let me see if there is anybody else. Because I think at the level of instantaneous luminosity, the design is not so far from the standards of other machines. So does it mean we are already, even though with one bunch, we are already discussing a level of luminosity that it's more or less what we are seeing in other machines, and we should not expect any significantly larger luminosities, because maybe of reasons like this, that going down in emittance eventually will be not so advantageous, or maybe the number of bunches you can make are not so many. So how much space do you see, even assuming a couple of miracles as in units that are often used?
At the end, we're limited by collective effects. So whether that, at the moment, we can see some limits in collective effects coming from the cooling system, maybe there will be some limits which we find in the high energy system as well. And then as with the LHC, then that in the end limits the luminosity. So to be seen, yeah.
We keep doing our plots 100 TeV and thousands of autoburn. Okay.
Absolutely.
No problem. All right. Is there any more questions or comments on this or other things?
Understand if I understood. So the reason for having one bunch in the current scheme of the muon collider is the collective effects.
It's to get to the highest luminosity. So let's say in the place where we're limited by protons on target. Okay, so it's really we know how many protons we can get to a target. Then we want to get as many protons onto a target as possible, get all of the resultant muons into one bunch and collide that bunch with another bunch. So if we find out, for example, that we have collective effects limitations, then maybe we may find that there's an optimum which is more than one bunch. If there are collective effects limitation at the low energy, or in the universe where we find that we can do more than, we can have a more powerful proton driver because the proton people get better at doing their job. I'm a proton person with my other hat on, so I'm allowed to say that. Then maybe we end up with more bunches for that reason. So yeah, we're to be seen.
But this is related to the fact that the emittance of the muon beam is going to be larger than a typical emittance of other beams that we know today.
Yeah. But in the end, I think it's everything Elias was telling us will probably be the limit, right? So yeah.
Okay, I think we can thank Chris once more.